battling fierce currents to build underwater piers. Welcome to civil engineering's ultimate challenge, underwater construction. Can you spot the mistake made by the chief construction engineer here? This error will lead to a catastrophic failure. Even though we call it underwater construction, modern engineers aim to avoid water entirely when building submerged structures. To construct effectively in a dry environment, the first step is to build a temporary dam, known as a Cofferdam, to isolate the area.
Working directly underwater is not a practical method for construction. The next challenge is how to build this Cofferdam efficiently.
The initial step involves erecting guide piles with a pile-driving hammer machine. These piles are crucial for accurate positioning.
These guide piles provide essential guidance for the precise construction of the Cofferdam, ensuring proper alignment.
Workers then drive numerous sheet piles into the soil using the same machine. These piles feature interlocking connections. This clever interlocking design at both ends of the sheet pile sections significantly minimizes water leakage, crucial for a dry workspace. The sheet piles are driven deep beneath the ocean bed until they firmly anchor into the solid bedrock layer.
Piling proceeds from the corners to the center, a strategic order that helps maintain consistent alignment throughout the Cofferdam.
Have you noticed the special feature of the pile-driving hammer? Simply pushing sheet piles down would cause them to buckle.
To effectively penetrate the soil, the machine utilizes powerful vibrations. Observe the rapid, subtle movements it generates.
The unique design of this machine incorporates two counter-rotating eccentric weights, which are key to its vibratory action.
These eccentric weights induce vibrations, allowing the machine to drive the sheet piles deep into the seabed with precision.
A barge, a flat-surfaced ship, is essential for transporting heavy machinery and various components to the construction site. Now, we are prepared for a crucial phase of the project, pumping out the water from inside the Cofferdam. Before proceeding with water removal, the engineers had a vital task: conducting a comprehensive geotechnical study of the seabed.
This detailed study of the soil was crucial for selecting a site capable of supporting the permanent bridge structure's load.
The most common method for assessing soil strength is the in situ cone penetration test, which accurately measures resistance.
The CPT device is carefully positioned on the ocean bed, ready to begin its penetration and data collection.
The conical tip of the device penetrates the soil, while internal sensors transmit friction and soil resistance values back to the surface.
Penetration continues until the bedrock is reached, marked by a sudden, significant increase in resistance values.
This valuable test allows engineers to determine the precise depth to which the sheet piles must be driven for optimal stability. Returning to our project, as the water level inside the Cofferdam lowers, you can observe water leakage between the sheet piles.
This leakage is caused by the differential pressure of the water. Single-layer sheet piles are failing under the stress.
To counteract this, we need to reinforce the Cofferdam by doubling the sheet piles, creating a stronger barrier.
The space between these double sheet pile walls is then filled with granular material like sand or gravel to prevent leakage. This double-layered Cofferdam, filled with granular material, effectively resists water leakage between the sheets. With the water now fully removed, there's no visible leakage. But watch what happens next. Oh no! It collapsed! The entire Cofferdam collapsed inward. Earlier, with water on both sides, the forces were balanced. However, once the internal water disappeared, a massive inward force was unleashed, causing the Cofferdam to be destroyed.
This inward collapse can be prevented by installing a robust bracing frame structure along the sides of the sheet piles.
The bracing frame system consists of key components: wales, struts, and braces, which provide internal support. These horizontal struts are bolted to the wales, providing crucial lateral support to resist inward movement of the Cofferdam walls.
Now, the Cofferdam is super strong and has firmly reached the bedrock, ready for the next construction phase. Let's proceed to dry the water inside. Can you anticipate what will occur next in this crucial stage?
This containment model allows us to observe the flow dynamics in real time. Notice how the liquid interacts with the sand layer right here.
We start the extraction here, and as the water level drops, the sand compacts. This clearly demonstrates how liquefaction causes...
By carefully reducing the water level, we induce a change in the stress state, resulting in these visible U-shaped deformation patterns within the sand layer. The same phenomenon will occur within our large Cofferdam when the water is pumped out, creating similar pressure changes.
To manage this, we must continuously pump out the seepage water. If the soil above the hard strata is removed and concrete is poured onto the hard strata, our underwater construction project is halfway complete, forming a solid base. This is known as the concrete seal course technique. It acts as a strong footing, effectively preventing any further water leakage.
Let's observe the process. Soil is removed from the Cofferdam using specialized clamshell buckets.
These clamshell buckets are efficiently operated by an excavator, making the soil removal process look quite impressive.
The next critical stage is the concrete seal course. To ensure a strong bond with the bedrock, piles are needed.
The vibrating hammer machine helps push hollow steel pipes into the bedrock, creating the necessary foundation for the seal course. The hard rock within these steel cylinders is then efficiently removed using an auger machine, clearing the way.
Now, reinforcement bars are positioned within the cavities, and concrete is carefully poured to form the foundation. Now, reinforcement bars are positioned within the cavities, and concrete is carefully poured to form the foundation. Since seepage water is always present at this base, the seal course concreting is performed using the specialized Tremie method.
A thick plug is installed at the bottom of the Tremie pipe to prevent water from mixing with the concrete during pouring. After some time, the pipe is lifted with a jerk, allowing the concrete to pour down and releasing the bottom plug. During this process, the Tremie pipe's discharge end is continuously submerged, ensuring the concrete doesn't mix with seepage water.
The concrete, being poured continuously, is less likely to mix with the surrounding seepage water, maintaining its integrity.
With the concrete seal course now complete, we can proceed with the remaining construction work, knowing the base is secure.
Workers meticulously lay out a skeleton of high-quality reinforced bars, forming the footing shaft for the bridge pier. As the bridge pier structure will remain submerged, engineers ensure only the best quality materials are used for durability.
The structure must withstand immense water pressure and the bridge's load, requiring robust construction. As the bridge pier skeleton progresses, concrete is poured into the structure, gradually building its solid form.
Once concrete pouring is complete, the structure is left undisturbed for 14 to 28 days to achieve full strength. With sufficient strength gained, the Cofferdam is no longer needed. Engineers carefully cut the sheet piles at this level.
Removing the Cofferdam below the concrete seal course could compromise the entire structure's strength.
And here it is, a strong bridge pier, ready to support a heavy bridge, thanks to meticulous underwater construction.
The key differentiator for us in the market has been our approach to sustainable growth, particularly in the tech sector. By focusing on these key metrics, we can significantly improve our market position and ensure sustainable growth throughout the next fiscal year.
From the bottom of my heart, thank you for considering our educational project. Together, we can make a real difference in the lives of these students.
From all of us here, thank you for joining us. Have a wonderful evening, and goodbye for now.